Hey everyone, welcome back to The Explainer. Today we're doing something I find absolutely fascinating. We're going to bridge that massive gap between high-level, abstract quantum mechanics and a highly tangible physical machine that literally changed the world. We are unpacking the physics and the engineering of the laser.
And it really all boils down to this one defining question. How exactly do we take scattered, chaotic, random light, the kind of light that just bounces around your room from a standard light bulb, and engineer it into a perfectly focused, enormously powerful laser beam? Well, the secret lies in figuring out how to trap light, contain it, and essentially force millions of individual photons to march in perfect, organized unison.
Here's our roadmap for today. 1. Inside the laser cavity. 2. The magic of mode locking. 3. Anatomy of a ruby laser. And 4. Achieving population inversion.
Okay, let's dive right into this. Section 1. Inside the laser cavity. Trapping a photon.
So, to actually trap light, physicists use an optical resonator, or what we call a laser cavity. And the most important metric here is its Q factor, or quality factor. Mathematically, it's just 2 pi times the energy stored in the cavity divided by the energy lost in one oscillation cycle. But honestly, just think of the laser cavity like a leaky bucket, but instead of water, it's holding bouncing light between two mirrors. A high Q factor means a low loss cavity, a really tight bucket. But here's the catch. It can't be perfectly sealed. A tiny, precisely calculated bit of light has to leak out through one of the mirrors. And that intentional leak, that's our actual laser beam. Because of this high Q factor, something pretty incredible happens to the light trapped inside. In a typical theoretical low-loss cavity, let's say with mirrors that are 98% reflective, a photon takes about 3 nanoseconds to transit across the space. But because it bounces back and forth so incredibly efficiently, its actual lifetime inside that cavity is around 150 nanoseconds. It lives 50 times longer than a single trip takes. And this extended lifetime is absolutely crucial. It's what gives the light enough time to build up and amplify.
Section 2. The magic of mode locking. Organizing the photons.
Now, what's really interesting here is we've trapped our photons, sure, but how do we organize them to pulse with incredible power? You see, a laser doesn't naturally produce one single perfect wave. It oscillates on many different frequencies, or modes, all at once. Usually, these frequencies have completely random phases. They're totally out of sync. They crash into each other, they cancel each other out, and the resulting light intensity over time is just chaotic random noise.
But then we introduce a technique called mode locking, and the chaos just vanishes. By forcing all those different frequencies to adopt a definite, locked phase relationship with one another, the waves beautifully interfere constructively at specific, repeating intervals. The chaotic noise suddenly becomes a brilliant, evenly spaced train of intensely powerful light pulses.
Let's slow down for a second and visualize the math here because it's super elegant. Imagine complex rotating vectors representing the different modes. Basically, think of these vectors as runners on a circular track, all running at slightly different but mathematically related speeds. Most of the time, they are scattered all over the track, totally out of sync, giving us effectively zero output. But because their speeds are perfectly staggered, there is one precise fraction of a second where every single runner aligns perfectly at the starting line. At that exact microsecond, their energies combine into one massive, synced-up wave, and boom, that is a mode-locked laser pulse.
Let's move on and see how this builds into something physical. Section 3. Anatomy of the ruby laser. Maimann's 1960 invention. So it's time to zoom out from the theoretical math and actually step into Theodore Maimann's laboratory back in 1960. We are looking at the world's first successful laser, the ruby laser. And honestly, it is amazing how elegant the physical engineering is compared to the dense math we just looked at. Right in the center is the laser medium. It's a single cylindrical crystal of pink ruby, which is just aluminum oxide doped with a tiny percentage of chromium ions. Wrapping entirely around it is this massive helical xenon flash lamp, literally the exact same kind used for high-speed photography back in the day.
The pure brilliance here is how the physical hardware so perfectly mimics our earlier equations. Those theoretical mirrors we talked about for our cavity Q factor, Maimann created them simply by polishing the flat ends of the ruby crystal and literally painting them with a silver coating. One was fully silvered, and the other was only partially silvered to let our beam leak out. The abstract concept of pumping energy into the system, that takes the physical form of that blinding xenon flash lamp. And our trapped photons are physically bouncing back and forth right through that chromium-doped crystal.
Section 4. Achieving population inversion, the critical mechanism.
So, how does a blinding flash of white light actually force these chromium atoms to create a concentrated beam? Well, it happens in 3 distinct quantum steps. First, the xenon lamp fires, releasing thousands of joules of energy in milliseconds. The chromium atoms inside the ruby specifically absorb the green and blue light. This massive influx of optical energy excites the electrons in the chromium ions, violently bumping them from their comfortable ground state, which we'll call E1, all the way up to a highly excited energetic state, E3.
But they can't stay there. Within about 10 nanoseconds, those electrons drop down to an intermediate state, E2. But here is where the absolute magic happens. E2 is a metastable state. That means the electrons get stuck there. Instead of dropping immediately back down to the ground state, they just hang out in E2 for about 3 milliseconds, which, let's be real, in quantum terms, is an absolute eternity. So the crucial point is this. Because the flash lamp is constantly pumping electrons up, and they are all getting stuck at E2, we suddenly have more electrons in the excited state than in the ground state. This highly unnatural bottleneck is called population inversion, and without it, a laser is literally impossible.
And this brilliantly illustrates the climax of the entire process. That population inversion is totally unstable. Eventually, one single electron at E2 drops back to the ground state, releasing a red photon. That photon travels down the ruby rod and hits another excited chromium ion. But instead of being absorbed, it stimulates that second ion to release its photon early. Now you have 2 identical photons traveling perfectly in phase. They hit 2 more ions, making 4. 4 makes 8. Because of those silvered mirrors on the ends of the rod, this wave of in-phase photons bounces back and forth, triggering millions of excited chromium ions and a massive optical avalanche.
The payoff of this avalanche is spectacular. The abstract math of cavity Q, those complex rotating vectors, and population inversion, it literally manifests physically, bursting right out of the partially silvered mirror. Because of the exact atomic structure of chromium, the resulting beam is a blistering, completely coherent pulse of deep red, visible light vibrating at exactly 694.3 nanometers. This 3-level solid-state system can even be manipulated with fast shutters, a process called Q-switching. This prevents the laser from firing until the maximum possible energy is stored, which compresses all that power into single pulses reaching peak powers of several gigawatts. Just wild stuff. So, from an equation representing a leaky bucket to a brilliantly engineered red beam capable of cutting metal and measuring the distance to the moon, now that we know exactly how to turn invisible quantum math into a beam of solid light, it really leaves you wondering what other wildly abstract physical laws are just sitting in textbooks right now, waiting for the right engineer to build them into world-changing machines. Keep questioning, keep learning, and I'll catch you in the next explainer.